next word you hear. Do it. Do it.
Good evening, ladies and gentlemen. How are we all tonight? Doing well? Good. All right. Well, my name is Mark Razzie from the Public Services Office here, and just wanted to take a moment to say welcome to tonight's edition of the Von Karman Lecture Series. For the first time in the history of Mars exploration, a radar sounder has been used to probe below the surface of the planet. The Mars Advanced Radar for Subsurface and Ionospheric Sounding aboard the European Space Agency's Mars Express orbiter has been bouncing radar signals off of Mars and its ionosphere since June 2005, mapping the interior of the thick polar ice caps to depths as great as 2 miles, and has discovered large hidden craters below the surface. It is also probing the ionosphere, discovering complex structures and mapping the magnetic fields of Mars in exciting new ways. Tonight's speaker is the 2001 Mars Odyssey project scientist and the co-principal investigator for this amazing radar instrument. He is also a research scientist in JPL's Geophysics and Planetary Geology group. Working at JPL for the past 15 years, he has project experience on the Magellan mission to Venus, Space Shuttle radar missions, and 3 Mars orbiter missions. Interestingly, his degrees include a BA in music from Brown University and a PhD in Earth and Planetary Sciences from Washington University at St. Louis. Ladies and gentlemen, please join me in welcoming tonight's speaker, Dr. Jeffrey Plaut.
Well, thank you very much. It's a real pleasure to be here. Actually, I come here every day. What am I saying? But really, we are truly in a golden age. I guess maybe the second golden age of Mars exploration right now, and it is a heck of a lot of fun to be right in the middle of it. And among the things that characterize this new era of Mars exploration are new kinds of measurements, and that's what I'm going to be talking about today. It's a completely new way of looking at the surface of a planet, in that we're not just looking at the surface, we're also looking below the surface, in some cases way below the surface. And in the case of Mars, there's all kinds of goodies to be found below the surface, and we're just starting to understand what this kind of measurement is telling us. And so I'll just launch into it. I've got a lot to show tonight. Forgive me if I go a little fast. There will be plenty of time for those who are willing to make it all the way to the end for questions. But let me just start by acknowledging, you see all these logos down at the bottom of the screen. There are many partners involved in this particular effort called MARSIS, and I'll explain what MARSIS is. But I just want to make sure to, sorry, I've got a tangle of wires here. Make sure that I acknowledge all of the partners. And the key partners in this effort are from Italy, from the US, and from the rest of Europe. So we have the Italian Space Agency, the principal investigator. I am the co-principal investigator, but the leader of this experiment is from the University of Rome. And the department is called the Infocom department. We actually have a member from the department joining us here tonight. And the industry contractor that put a lot of the radar instrument together for us is Alcatel Alenia Space in Rome. Of course, NASA is behind the other half of the instrument. It's about a 50-50 collaboration between the two space agencies, Italian and U.S. Space Agency, with the leadership of the experiment development here at JPL, a lot of contributions from the University of Iowa. The Northrop Grumman Space Technology Group provided the antenna structure, and of course ESA, the European Space Agency, is giving us the ride on their spacecraft Mars Express. So MARSIS is an acronym. It's kind of an awkward acronym, but it says a lot about what we do. It's the Mars Advanced Radar for Subsurface and Ionospheric Sounding. And this is a picture, an artist drawing of the Mars Express spacecraft, and the most obvious manifestation of MARSIS is these long structures, which are the antennas. It's a radar system, and a radar uses radio waves, and we broadcast them and we receive them. We look for the echoes. And we use these two structures that tip-to-tip make up one antenna called the dipole antenna. It's 40 meters, or what's that, about 150 feet from tip to tip. It's a huge thing on a spacecraft that's only about 4 feet across on this little cube. And then this additional antenna called the monopole is about 7 meters long. So it's a radar. It's advanced because it's the the newest one, and it probes the subsurface and also the ionosphere. And I hope I'll have time at the end to tell you a bit about the ionospheric sounding, but I'm going to focus mainly on the subsurface part of the experiment. Now, this is part of course, the exploration program at Mars, and you may have seen or heard representations of this chart, which is that there are sort of four major themes that drive our exploration. There is the search for life. Is it possible that life exists on Mars or did once in the past? We want to understand how the climate of Mars behaves and how it's changed over the history of the planet. Of course, the story is written in the rocks, and that's the geology part of this equation. And eventually, we want to understand what does it take to put humans on the surface and have them survive and explore. All of these things can be tied together with one common theme, and that is water. Water. When was there water on Mars in liquid form? Where is the water currently? Primarily in ice form, we believe. What form is it? And just how much water did Mars have originally? How much does it have today? So we are using many dozens of tools right now at Mars to address these kind of themes, and in particular tracing it through the unifying theme of water. So those are the goals of the Mars Exploration Program. Here are what I call the robots of the Mars Exploration Program. And this gives you an idea of why I said this is a new golden age. Of course, the first golden age of Mars exploration was in the 70s when we had the series of Mariner and, of course, the Viking missions, very successful, the twin orbiters and twin landers. But about 20 years later, we started a new program, and we keep on chugging along, starting, of course, with Mars Pathfinder and the Mars Global Surveyor. All of the robots enclosed by this red box here are actually still functioning at Mars and are producing just an incredible treasure trove of data. Of course, we have MGS, Mars Global Surveyor, Mars Odyssey, which continues a very successful mission. This is the mission that's giving us the radar, the ride, the European Mars Express Orbiter. I'm sure you've heard that that NASA JPL's Mars Reconnaissance Orbiter recently entered orbit around Mars and is now adjusting its orbit, preparing for its science mission. And meanwhile, the two little rovers just keep on going and going and going down on the surface. So we have a grand total of 6 functioning robots in the vicinity of Mars, and every one of them is telling us something new every day. It's really quite remarkable. Okay, so now to follow this theme of following the water. Here is a one-page summary of where we know there's water on Mars today. H2O. Now, when I say water, I mean the molecule H2O. I don't necessarily mean that it's liquid, the kind of stuff that gets you wet. But there is water vapor in the atmosphere, and occasionally there are ice crystals, occasionally droplets. But if you took that atmospheric amount of water vapor, rained it all down on the surface, it would make a global layer, this global layer thickness of 50 microns. That's 50 millionths of a meter. In other words, it's hardly anything. It's barely a drop in the bucket, so to speak. On the other hand, there is the ground ice. This is ice that's frozen in the near surface, only within the upper meter of the surface, because that's all that this technique can measure. But the Odyssey neutron detectors and gamma ray spectrometer found that there is water ice in the upper meter from about 60 degrees latitude to the pole, both north and south. If you took that amount of ice and spread it out over the planet, you would get something like 14 centimeters. What is that? About a foot. I need help on these conversions. I work in the metric system. Half a foot even. Yeah, okay. So again, it's not insignificant. In fact, Mars is such a big planet, so you spread 6 inches of water across the surface, you actually have a few Lake Michigan's worth of water. In any case, the vast bulk of the water that we know about, the H2O that we know about, is in what's called the polar layered deposits. And this estimate of that global layer thickness, 22 to 33 meters, comes from something called MOLA, the Mars Orbiter Laser Altimeter, which is the topographic mapper on the Mars Global Surveyor. And again, this 20 to 30 meters of global ocean, it's not quite the amount of ocean that we have on the Earth. And in fact, it's not enough water to do all the work that we can observe water has done across the surface of Mars in its history. That is, all of the channels that have been carved, all of the material that's been moved by water erosion. Estimates are that it takes hundreds to maybe a kilometer of global equivalent thickness water to do all of that work. So even though this is the largest reservoir, and this is the main subject of my talk tonight, it is not all of the water that the question, where did all the water go? We still don't know where all that water went, and we're still looking for it, and this is one of the ways we're looking for it. But right now, this is our best knowledge. Now, what I think I'll try to leave you with by the end of the evening is that we need to make some changes on this chart because we've learned a few new things and we found water in a few different places than we knew about previously. So let's talk about the polar regions for a while here. Now, the poles of Mars have ice caps, but the term ice caps can be very confusing because it means different things to different people at different times of the year. So let me try to sort it out for you. These are images that were derived from Viking orbiter mosaic images. So it's a real picture of the planet, although it's been sort of treated a little bit by exaggerating the relief, the amount of topography, by draping it over this MOLA topography map. In any case, centered on the pole, you see the North Pole here and the South Pole here. These are summertime views. So when all of the winter frost and snow has gone, and that's primarily carbon dioxide or dry ice frost, there remains in both the north and the south these white patches, which are sometimes called the residual polar ice. And it's been determined from measurements actually back from the Viking time that this bright white material that's left on the north is primarily water ice, and this bright white material left on the south is primarily carbon dioxide or dry ice. Notice that they're very different in size. So when I say that there are 20 or 30 global meters thick of water ice, where is that? Well, you get a better picture now just looking at the topography alone. Okay, so these are height maps, elevation maps, and you can see the scales. The total amount of relief represented in each is about 6 kilometers. And what we talk about as the polar layer deposits are these higher standing patches of surface here in the south and here in the north that have, they kind of, if you can imagine the way this might look in 3D, that they're sort of a dome shape, although this one has kind of an asymmetric pattern to it. The highest peak here is about 3.5 to 4 kilometers above the surroundings in both the north and the south. And they both are about 1,000 kilometers or 600 miles in diameter. So all in all, about 1 million square kilometers. And when you add all of that up, you can take these topographic maps and calculate a volume for this material. That's how we get that number, 20 to 30 meters of global layer thickness. So we call these layer deposits, and we believe they consist of ice. And actually, MARSIS, I can say, is pretty much slammed the door and confirmed that they are, in fact, made of water ice. And why do we call them layer deposits? Well, let's take a closer look. This is now a view of the North Polar deposits. And here, this is in regions where there is this residual summertime water ice that sits on the tops of this layered material. Now here you don't get a real good feel for the layers. This, by the way, is an image that was acquired by the beautiful camera on Mars Express called the high resolution stereo camera. And the shapes of the terrain are, in this case, are draped over the topography from the MOLA instrument. If we go to the south, you can get a better view, and we have similar views also in the north, of why we call these the layered deposits. This is a visible light image, so a black and white visible image from the Themis camera on Mars Odyssey. And you see all of this striped or laminated terrain here. This is what we're talking about with the polar layered deposits. Here we're seeing the boundary between those layers, which sit higher, and the surroundings or the substrate, which sits lower. So there are a few craters you can see here. Here there's a little lobe of this layered material that sits partially in this crater. And you can see as this material gets eroded back, it exposes the many layers, the internal strata or stratigraphy that's inside this unit. Now, in this image, we're only looking at a height difference of about 1 kilometer or so, but as you climb up these things, go another 500 miles from the edge to the center, 500 kilometers or so, then you'll see that you've gone gone up over 3 kilometers. Now just a little zoom in here so you can see the beautiful detail. Now in the optical images that we've received over the years, especially from the Themis and now the Mars observing camera on MGS, we see that these layers exist all the way down to the finest resolution that the camera can see, so all the way down to a few meters. Sometimes they come in packages that are a bit thicker. We also now have another way to look at these layers with our radar system. Okay, so now what is MARSIS? What does it do? Well, again, as I said, it's a radar. So here we are flying along in orbit above Mars, somewhere between about 300 and 1,000 kilometers above the surface. We transmit radio signals, and they're very special kinds of coded pulses. We transmit about 100 of these pulses every second, and then we constantly switch our instrument from transmit mode to receive mode, so we listen for the echoes. Now, as we fly over, every second we image a new patch of the surface. And that patch, each of these little footprints on the surface is about 5 kilometers apart, and across the track, depending on the characteristics of the surface and our altitude, it's about 10 kilometers. So this is essentially the spatial resolution on the horizontal scale of our system, 5 to 10 kilometers. We use radar signals at 4 different channels. We can select any 2 of these 4 at any given time. And these are in the megahertz, millions of cycles per second range, which is actually a very low frequency for radio waves. In fact, the only place that this kind of low frequency system works on the Earth is when you're flying or dragging a radar at a very low altitude over the surface, something called ground penetrating radar. We can't fly a radar like this and get any echoes from the surface of the Earth, because the Earth's upper atmosphere, ionosphere, which Mars also has, tends to repel these waves. In any case, the wavelengths, if you're familiar with radar imaging systems, the wavelengths are measured in centimeters. Here we're measuring our wavelengths in tens of meters. In fact, over 150 meters for our longest wavelength signal. The reason we want to use these long waves is long waves penetrate materials more easily. So we were trying to see as deep into the subsurface as we possibly could. So for each of these footprints, we transmit the echoes, we receive them, they're recorded on board the spacecraft, there's some processing that goes on, they get transmitted back to the Earth maybe a day later, we do all kinds of other magic on them. Eventually we turn them into what we call echo profiles, and the profiles generally will have a strong echo from the surface, which is represented here, and then some time goes by, and then maybe there's another blip at a later time, and that other blip is what we're looking for as evidence of some other object or layer or material in the subsurface. And what we do is we take each of these echo profiles, we kind of stack them all side by side and generate this image called a radargram. So I'll be showing a number of these radargram images. Here in this case we see the echo from the surface, so the sky is above here. Here is the wave intercepts the surface, it goes a little bit farther and it bounces off of something else, and that is our subsurface boundary. And here actually is a larger view of that same measurement, and here we are on our friend the North Polar layer deposits. So down here is, again, a topographic map, and the total amount of relief here is about 2 kilometers from the purple up to the orange, and this red line indicates the ground track of our radar system. So as we're flying along here, it looks like we're basically just getting one strong reflection. That's the reflection from the surface of this material. As soon as we get up to this elevated terrain on the layer deposits, we continue to see an echo from the surface, and it's closer to the spacecraft, so it sits a little higher in this cross-sectional view. But in addition, we see this lower echo as well, and that is a subsurface detection. In this case, our interpretation is that this lower boundary here is actually the boundary between this icy material of the layer deposits and the surrounding material that is also underneath the icy material. And in order to see a reflection, we need to have a contrast in the electrical properties of those materials. And ice sitting on top of a rocky or a gravelly or dusty surface provides exactly that kind of contrast that we would predict would create this kind of signal. So basically what we're saying here is that we can see right through this icy layer deposit, And in fact, by measuring the time that it takes for the signal to go through, we have determined that at this point right here, the maximum penetration in this particular example was 1.8 kilometers. We saw through it just like it wasn't there almost. Of course, we do see that it's there because we get a reflection from the top, but a huge fraction of our signal goes right past that first interface and is picked up down here. The fact that our signal goes right through, it's not attenuated, it's not slowed down, or the intensity is not diminished, and that actually is consistent with an idea that there is very little dirt mixed in with this ice. It's actually very clean water ice. And the fact that it appears striped in the optical images is probably basically the addition of just a very small fraction of dust into the ice. We don't see any evidence that there's liquid water down here at the base. It's actually very close to a very cold surface, so we wouldn't expect that there would be liquid water at this shallow a depth. Also, what's interesting is, although you can't tell from this picture, this lower surface actually sits right at the same level as the surface outside of the deposits. It appears that it's deeper here, but that's actually sort of an optical illusion because this image is in terms of time delay, not in terms of distance. If we correct the distance for the delay of the signal in here, the planes in the northern latitudes just go straight through underneath. And so there's no deformation or down warping of the crust of Mars, even though it's got several kilometers of ice sitting on top of it. This is in contrast to the continents on the Earth. When the ice sheets come over the continents of the Earth, they sink. It's an isostatic effect where you add more mass, there's a mantle underneath that gives way, and the continents and the ice on top tend to float on that mantle. You put more mass on there, everything goes down. Then when the ice sheets retreat, I hope I said that right, as you saw in the movie Ice Age 2, The Meltdown, the land tends to rebound back up because it's been depressed, and when that load is removed. Actually, I don't know if it shows in that movie, but I want to see it to find out. But on Mars, we don't see that effect. And so that tells us that there is a very strong upper layer to Mars, the layer that we call the lithosphere, the combined crust and the upper mantle. And it has a large elastic thickness. In other words, you can't depress that like you would, say, if you were standing on the edge of a diving board by just putting more weight on it. Okay, now let's move to the south because that's where we have the really interesting data. In 3 days, Mars Express actually only visits the planet 3.5 times a day on average. It's in a long orbit. And so over the course of 3 days, we built up a little map that consists of 11 orbits. And in this case, we acquired data over that group of 3 days. This was sometime in January. And so we built up this little net over the South Pole. Well, actually, we've been doing this for 4 months. And so, in fact, we have this incredibly beautiful, nearly complete coverage of the south polar region of Mars with our experiment. And we are very grateful to all the people who made this happen, from our coworkers on our instrument team to the people who manage the spacecraft back at ESA, the folks at the DSN and at the ESA ground stations who managed to collect all of that data. All of the folks involved, it's just been an incredible success, and we're just so pleased that our experiment has started out with such a bang. Okay, so the next number of images that I'm going to show, again, I have the radargram image here on the top, and down here is the topography image. And the distance between these ticks, I don't have the scale bars, but the distance between these ticks is always 500 kilometers. So here we have a little bit of annotation on this diagram, so you can sort of have a point of reference when I show these. Okay, so again, this is the radargram, and it's like a cross-section, okay? So this is the sky, this is the surface, and this is potentially the subsurface. It's places where echoes come later than the surface. And so up here is the plains surrounding now the south polar layer deposits. Right here, this is a very similar kind of signature to what we saw in the other example in the north. We see the layered deposit, south pole layered deposit surface here, and then we also see this lower boundary here, again diving down, although again that's an illusion. And in addition, here in this picture, the center of this is the ground track. Again, here's the scale bar, 500 kilometers, and the vertical scale is in time in microseconds, but it's enough to just remember that in this case it's 3.3 kilometers from the surface down here to this lower boundary, what we call the basal interface, the boundary between the icy layer deposits and the substrate, the lower material. A couple of things that probably you're wondering about in this image. One is there seem to be some stripes here in the middle, and I'll get to that. You're not imagining that. Also, this interface goes along here just like this, and then boom, it ends. And that's a mystery, and I'll take any suggestions as to why that might be. We have some ideas, but none of them are really compelling or satisfying, and it's going to be very difficult for us to choose between various hypotheses. In any case, we believe this boundary represents, again, the contact. So these icy deposits, whenever they were created, probably sometime in the last 10 to 20 million years, this is where they started to pile up. This was the surface before that, and nobody has been able to see that surface until now. Here is another example in a different area. This is in an area where it's not quite as thick. It's about 1.5 kilometers here, very smooth part of the deposit. And here, zoomed in, you see this really nice multiple sets of reflections or layers. Here we have 7 or 8 different of these reflectors, so they're a few hundred meters apart, apparently. And we'd like to understand what it is exactly we're seeing when we see a half dozen or so of these reflectors in this layered material. Okay, now looking at that lower boundary, what we can do is we can basically make a map of its elevation. If we understand how fast the wave is moving through the ice, and we have a pretty good idea of how fast that speed is, we can translate the time delay from the surface to that subsurface boundary into a distance, and we have pre-existing topographic maps, so we can subtract off that distance and wind up with a map of the base of the layer deposits themselves. So these are the steps we go through. We measure the time delay from the surface to that lowest subsurface reflection. We convert that thickness we convert that time to a thickness, assuming the dielectric or the speed of the wave. Then we get all of the elevations from the altimetry experiment for each of these footprints, subtract that off, and then what's represented then in the blue dots here is a topographic map of the bottom of the deposits, whereas up to now all we had was a map of the top. And what you can see here, again, this is a profile, so it's highly exaggerated vertically. You can see there's about 3.5 kilometers of relief on the deposits here, but again, you can see that our mapped lower boundary is perfectly flat, topographically flat. It's not depressed by this weight of in this case, 3.5 kilometers of overlying ice. It's very important for the geophysicists who try to understand how does the crust and mantle of Mars respond to forces to see that this crust of Mars is presumably very cold, and there is not a mobile mantle at any shallow levels, anything like what we have on the Earth, where the mantle can be just a few kilometers deep under the oceans and maybe 10 or 15 kilometers deep under the continents. Okay, another bit of a puzzle that maybe also caught your eye is that this is a very bright reflection here, whereas the reflection from the surface of the deposit is not so bright. In fact, these reflections are just about as bright as the surfaces out here where there's no ice at all. Again, this hammers home the point that we're seeing right through this material. It's not absorbing much of our energy, and that, again, is consistent with the idea that it's very clean ice. But now, why would it be such a bright echo down there? Well, first we thought, well, we know liquid water has a very high reflectivity at these wavelengths in this particular geometry. Maybe we're seeing a melt at the base of this. There are things called wet-based glaciers on the Earth. There are portions of the ice sheets in Antarctica and in Greenland where by drilling down, or in fact using techniques like this from aircraft, we can determine that there's liquid water at the base. So we wanted to examine that possibility, but unfortunately it doesn't seem very likely for several reasons. First of all, just from first principles, it's very cold in the south pole of Mars. And in order to get down to a depth where the warmth of the internal heat of Mars is making things warm enough to melt that ice, you have to go up about 100 degrees centigrade in temperature. In other words, from freezing to boiling, the equivalent amount in 3 kilometers. There's no place on Earth where we have that geothermal gradient. where the temperature changes that quickly over that short of a distance. If that were the case, we would never be able to make deep mines. It would be too hot to work down in the mine. Also, from our data, we can tell that this bright surface is bright right here, it's bright right here, it's bright all the way along here. And in fact, if the reason it was bright was because it was wet, then it has to be wet just 100 meters below the surface. And that's even less likely than it being wet several kilometers below the surface. So in general, we don't feel like we have any robust evidence, any strong evidence that shows that there's liquid water at the bottom of these deposits. But what we've done is we can measure remember each row, or rather each column in these images, in these radargrams, is actually a profile, an echo trace representing one footprint. And so if we extract that echo trace, we get something like this. So here's time, and here's power, and here's the echo from the surface. And then as you can tell, the basal interface is giving us a brighter echo. And in radar speak, it's 9 dB brighter. That's a lot brighter. It's exactly the opposite kind of relationship we would expect. Generally, the surface gives the strongest return, the wave gets attenuated, it gets diminished as it goes deeper, and so the lower boundary would be a weaker of the two echoes. In this case, it's the brighter, and the only reason I show this is that it's telling us that there's something rather unusual about the upper surface. It's not that there's anything remarkable about this lower surface. This surface is just as bright as the surroundings, and we can see through the ice, and so we would expect it to be very bright. But this other upper surface is rather dim, and it's dimmer than what we would expect if that uppermost layer was pure water ice at a density of 1, which is, the natural density of water ice, slightly less than 1. It has to be rather less dense, or there may be a mixture of carbon dioxide, either chemically or physically, mixing in with this ice, although there's no way for us to actually solve that particular problem. But it's telling us that that upper surface is a little bit different, whereas the bulk of the layered deposits are most likely pure water ice. Okay. Another snapshot here. This is not a particularly remarkable example here, but what I'm going to show is some of our data in its full resolution mode. So this is the normal way we do it, and what we do is we actually sum. I mentioned we get about 100 pulses a second. We actually add all those pulses up on board the spacecraft because it's too much data for us to send back all of those echoes. And so we're basically reducing our data volume by about 99%. But for little bits and pieces, place to place, we can collect all of that original raw data. We store it in a buffer. We wait until we're far away from Mars. Nobody else is doing anything. We stream that data back to the Earth. And that's our full resolution data, which we call our flash memory mode, because that's the name of the device in the computer that holds it. And so here is some of our flash memory data now. It's for exactly this segment here, and you can see there's some hints of some layers. You maybe see a little bit of the structure. Here you can see we're looking at it now, that entire end-to-end piece. It's showing a little bit nicer. Let's zoom in a little bit, and here you can see this is the MARSIS data sort of in its full glory. This is every pulse. Now you see these kind of boundaries between, these are groups of pulses of about 80 each, and then there's a gap, and then there's 80 more pulses. But you can see many, many, many layers, and you can see all the detail. It's actually just a few hundred meters, about 200 meters from one row here to the next row to the next row, and then there's a gap of about 2 or 3 kilometers, and then we get another set of these full pulses. So it's really allowing us to dig in to the data. We've chosen just certain select areas where we get this full resolution data. We can't do it everywhere. It would overwhelm the telecommunications system on the spacecraft. But what we do is now we're taking this detailed look at the layers and trying to compare it with what shows up in the pictures. Try to understand what is it in the optical. Again, here this is Themis visible, and this is about 1.5 kilometers of relief. This is high, this is low. What is it that's changing in these layers optically that perhaps will give us a clue as to what's changing them electrically for our radar? Because our radar is responding to the electrical characteristics and in some sense to the geometrical characteristics of the materials of these layers. And I don't have the answer. This is work in progress, but I think what it's going to allow us to do is not only say, yeah, it's pretty much pure ice, there's just a little bit of dust in there. It's also going to give us another level of detail about what is it that causes these layers. Now, I should have said this a while ago, and maybe it's occurred to some of you, that we're interested in layered materials on Mars for the same reason we're interested in layered materials on the Earth, and especially icy layered materials. I'm sure most of you have heard about ice coring. Ice cores are used to decipher former climates. That's really the whole point. And a lot of the research that goes on Earth having to do with climate change, and there's an ongoing discussion about is the climate change that's happening now, is that part of a natural pattern or is it related to man's activities? And so to understand what the natural variability is, we go back into these ice cores and we look at how the different seasons, the different winters of ice deposits, which are remnants of the snow that fell that winter, how those change as the conditions on the Earth change, as the carbon dioxide levels change, as the oxygen isotopes change, the various, there are volcanic signatures in ice cores when certain volcanoes create, sulfuric acid and acid rain. Sometimes it has a global reach. And so there are all these different things that can be measured in ice cores. What we're doing here is we're basically measuring an ice core at Mars, but we're doing it from a distance. And we're hoping that at some point it's going to tell us something about the climate history of Mars. And this is water after all. So we're hitting two of those themes that are connected by water that I showed at the beginning, the climate history of Mars and the water itself, connecting those two by making these measurements and taking the whole ensemble of measurements from the optical data, from the compositional mappers, spectral data, and of course our radar system. Okay, now for some new H2O. Again, this is a topographic map, not quite as pretty as some of the others, but the red here basically is the outline of the south polar layered deposits, these icy deposits that we have no problem seeing through when we're mapping the base of them, et cetera, et cetera. Now, where there are these little band-aids over our ground tracks are areas where we also see layers in the subsurface. And this was not known that we would be able to see these layers. It's not a shock to any of us, but it's very exciting because these surfaces were not thought to be dominantly ice, whereas this material was pretty widely agreed to be ice, and we thought, well, we can see through it. Okay, great, we can measure the bottom. But here now we're discovering different kinds of layers and different kinds of material. And so for each of those ground tracks that I showed, I have a few of the examples, and where there's a yellow bar here, you can see this trace of a lower boundary of some kind. So again, this is the layered deposits, and sure, we have all kinds of structure and beautiful things to look at here. But now what I'm interested in is these areas adjacent to, and actually in some cases some distance away from the layered deposits, where we see a second boundary in the subsurface. Here, again, 500 kilometer scale, so in this case we're looking at about 1,000 kilometers as you move away. Remember, the layered deposits are about 1,000 kilometers in diameter, so going just as far away from the deposits, we see good evidence of layering here also. And in some cases, there's nothing obvious in any of the other data sets that says there ought to be layers here. So this is, here we're really peering into the unknown. We're looking below the surface at features that really are not accessible any other way. Here is another example, some of these thin layers. In general, we estimate these are a few hundred meters to maybe 500 meters deep, these lower boundaries. And here's one more example. And when we map out the positions of these, we find that, at least from our preliminary look, that it's a very large area. In fact, this area is equivalent to the area of the layered deposits themselves. The amount, the thickness of the material is not as great as the layered deposits. As I said, it's a few hundred meters to half a kilometer, something like that. But if you add all that up and you assume first that it's dominantly ice, let's say it's 75% ice, and we do believe they are mostly ice, then you've identified another reservoir of H2O on Mars that really nobody's been able to put their finger on before. And that amount of ice, in this case, if you added up all of those, you would probably get another 5 to 10 meters of this global layer. So that's why I said at the beginning, we probably need to add another line on that chart, not just the layered deposits proper, but also these other layered materials. And we see them predominantly in the polar regions. That's one of the reasons why in polar regions we know are a trap for volatiles, being water ice and CO2 ice. It's one of the reasons why we believe strongly that there is a lot of ice in these units. There is other evidence related to the geology and the mapping that people have done over the years that says a lot of this material was probably either previously extensive layered deposits or in fact melted material that then froze in place during catastrophic melting episodes. Okay, now I didn't talk about this up to now, but a major problem that we deal with in processing and interpreting the MARSIS subsurface data is something called clutter. And what we do is we need to reject the clutter because the clutter is a kind of noise that can confuse us. So here again is a MARSIS radargram, and here is a model of the radargram that we would expect to see if there was no contribution from the subsurface. Okay, and so that's why here on the layer deposits you don't see anything except maybe a few little lines here. But basically all of this beautiful structure in here is not predicted from the surface topography. It's something that's inside the planet. On the other hand, down here you see all kinds of structures and features and little loops and U's and straight lines and things like that. These are all what's called clutter. It's signals that arrive at the same time as signals would from the subsurface, but they're coming from off to the side because our wave spreads out like a sphere. And so at any given time, there is a contribution coming from the side of our ground track, not from directly underneath us. And if there's rough topography, you see it, and it could look like, so it could fool you into thinking you're looking in the subsurface. Here, these are mostly these impact craters. You can see here there's sort of a one-to-one relationship. And in fact, a lot of this structure is represented in our image. Well, the reason I show that is because early on in the mission, we came across an area. Now we're in the northern mid-latitudes, the northern lowlands, okay, not in the polar regions, so we're in a very different place on Mars. And as we flew along here with the MARSIS data, we came across this very flat, smooth region. This is the outflow region near where Mars Pathfinder landed. And we looked in our MARSIS data, and all of a sudden, things started going crazy. We saw this line here. We saw these loops, these concentric loops, and so we ran our clutter model. There's nothing to speak of in there. There's a few little dots from a few little bumps and craters, but nothing like this structure is predicted. And you can pretty much see that also from the topography map. It's flat there. So what were we looking at? Well, turned out we had two parallel orbits. They come every 11 orbits. We get these parallel tracks about 50 kilometers apart. And sure enough, at the exact same latitude as we crossed this area, we saw in both this orbit 1892 and 1903, we saw these parallel or concentric parabolic kinds of structures. And in this one, we also saw this line here. We didn't know what we were looking at. And we think we have an idea now, but we could be totally wrong. It was good enough we slipped it past our colleagues in peer review and got it published in a journal, but we don't really know whether we're right or not. In any case, I'll tell you the story. What we do is, now remember, these are in time delay, and we thought, well, are we seeing in the subsurface? Are we seeing gigantic bowls in the subsurface? Actually, these bowls would have to be 10 kilometers deep. It's ridiculous. We never would have anticipated that we could see anything as deep as some of these signatures. So we had to maybe play around and try another approach. What we did was we said, okay, even though we know it's not clutter coming from topography, let's just pretend it is and see where it lies on the surface. And so that's what we do here, and it's a little hard to see, but just trust me, these little Rorschach blot pictures are the radargrams reprojected to the positions where all of these features would be if they were coming from nearer the surface. And we don't know if they're coming from the left or the right. We don't know where they're coming from, but we're just guessing here. And so there are little mirror images here. What we found, though, was that we took these two orbits and we did these ground projections, and it turned out these arcs started to line up on top of each other. What that was saying to us is we were seeing the same thing twice from two different angles, like a little stereo view. Also, our hypothesis that these are near the surface actually may be close to correct. And the way you would get this kind of signature, we did some modeling that says as you're flying along and you're flying over a flat floored hole in the ground, like an impact crater or impact crater basin, this is something like what you might expect to see. You see maybe an echo from the floor. That's this line. And at earlier and also at much later times, you see echoes from the rim, from the sides. But there's no crater there. It's a flat surface. So what we are claiming, our interpretation is that there's a crater there, but it's buried just below the surface. It's filled in, and then there's a little bit of a layer on top to completely hide it from any other sensor, but our radar, our plucky little radar, can go in there and see just below the surface, and it sees it as clutter. But it's not, in this case, it's not clutter that's annoying noise to us. It's clutter that has valuable information because it's allowed us to discover an impact basin that's 250 kilometers in diameter, one of the largest ones in all of the northern plains of Mars. And that's important for the people who use craters to try to understand the ages of surfaces. They use craters to understand how different layers build up over the course of time. And so here what we've done is we've taken the ground tracks and we drew in those arcs in their position, and the ones that matched up are shown here, and you can see these red and these white ones line up almost perfectly. So very clearly there were circular features somewhere near the surface. They make a nice little circular pattern here. The story mostly holds together. But there's an interesting little twist on top of it. One of these also has this line right here. What is that? Well, actually, that can't be from clutter from the sides, because you would have to have some wall exactly parallel to your ground track. It's very unlikely, and there's no evidence from any of the other data sets that that kind of structure exists. So, in fact, this is exactly what you would expect to see if you have a deep boundary, a layer. So basically, the way we interpret this, as I showed in the model here, is that you've got the floor of the basin and you've got the rim. But here, instead of it being exposed, it's buried. And our estimate is that it's 2 to 2.5 kilometers deep. And again, here, it's not as bright a reflection as the bottom of the layer deposits compared to the surface, but it is still very bright, surprisingly bright by our measurements. And in fact, what it requires is that the material in between the surface and the floor of this basin down here, 2.5 kilometers deep, again, it doesn't attenuate the signal very much. It probably has a lot of ice in it. In fact, our estimate is that it's got to be 80-some% ice in bulk on average through there. So that's what's being said down here. Planar reflector, 2.5 kilometers deep, low loss in the volume, and perhaps it's ice-rich. This is, again, perhaps, I'm putting all these caveats on it, another new part of the reservoir of H2O on Mars that nobody's been able to detect before. So we're very excited about that. We're going to go back and revisit this area when we get a chance. This was from early in the mission. We only got a few glimpses of it, so very high priority target for future observations. Finally, some very new data. Our orbit is migrating, is drifting away from the south polar regions, and now we're starting to look at the equatorial areas, and the equatorial areas, of course, where the rovers live. And it so happens that we came very close to the Opportunity landing site, shown here in the topography map. Sorry for lack of scales, but again, this is 500 kilometers in the zoom in here. So here's Opportunity. Our ground track is across the middle, and we see perhaps a boundary here in the subsurface below the Opportunity landing site. Again, perhaps this one needs more work. But for sure, as you go north, about 500 kilometers north, there's some kind of very complicated, very dramatic structure in the subsurface up here. We need to try to understand what are these materials that we're seeing through, how are they related to the materials that Opportunity has studied up close, is there any relationship? And what is that telling us about the history of this area? What can we add to the story that the rovers are telling us about this part of the planet? Very interesting, very exciting. Of course, the conclusions that the Opportunity team have come to is that the bulk of the sediments beneath Opportunity were laid down in water. They represent lake sediments. They've been reworked by the wind, possibly wetted again by groundwater, but there's a big role for water in these sediments. Presumably, something similar has happened over here. For some reason, we're seeing right through, and we're seeing multiple layers with MARSIS. I don't have any further answer than that. Okay, now, quickly, before we wrap up, I want to talk about a kind of esoteric part of this whole story, which is the ionospheric studies. Now, the ionosphere is really just the top of the atmosphere of a planet. It's the region where the solar wind is interacting with the materials, and the gravity is so weak that there is a plasma rather than air, basically. Plasma meaning that the molecules have become ionized. They've lost their electrons, they're free electrons, it's charged. It's susceptible to magnetic fields. It does all kinds of good things by funneling or repelling other charged particles that come in. It's part of our shield here that helps protect life on the Earth. And it's a very interesting feature of the upper part of the Mars atmosphere. It turns out that the frequencies that we use on MARSIS can probe and kind of dig in and get their fingers on the ionosphere of Mars as well. And so that's why we have the I in our MARSIS acronym for ionospheric sounding. It's not too different from what we do with the subsurface sounding, but it's different in a few ways. And this is sort of in a sense, a radargram from the ionospheric experiment, but this is actually a snapshot that was acquired over the course of 7 seconds. It's basically one observation by the ionospheric typical. That's spelled right. Okay. So this is as a function of our frequency, and this is our single megahertz range of frequencies. And this is, it's oriented the way the others are, where this is the sky, this is actually the spacecraft position, and this is time going down. In this case, though, we're looking at things above the surface, and right here is where we get the surface reflection. So this is an observation that was made from an altitude of about 800 kilometers, and sure enough, the apparent range, the apparent distance from the spacecraft to the ground is 800 kilometers. But as you go lower in frequency, we lose that ground reflection, and instead we get a reflection off of the ionosphere. And that's really what this part of the experiment is looking at, is these reflections and how they change as we change the frequency of our pulses. And where the ionospheric echo, it kind of it bends over here, and where that meets or intercepts the ground reflection, this is called the ionospheric cutoff. Basically, it's saying no frequencies lower than this get past the ionosphere. Okay. So here's something interesting. This is a case where now we don't see that ground reflection at all for some reason. Something about the ionosphere is preventing all of our signals from getting through. But we also see the ionospheric echo here, and then some other echo here, which is, okay, the altitude of this is about 400 kilometers. And so the ionospheric echo here is around 300 or so, just where you'd expect it to be. This echo is coming from basically a distance that would be below the surface, and it's not below the surface. What it is it's clutter. It's clutter coming from some off nadir position, somewhere off to the side, and it's creeping in to the detector of the ionosphere. And how would that happen? Well, this is just a kind of a schematic. That first echo comes from the ionosphere boundary directly below you, and then some later echo, which maybe isn't quite represented here because this looks like it's closer to the spacecraft, but it's farther away from some tilted part, some mountain in the ionosphere or bump in the ionosphere that's creating this clutter signal that comes later, and that's why we get these two echoes. Now, how would you do that? How would you distort the ionosphere into bumps? Well, you do it with magnetic fields. And Mars, it turns out, has a very complicated magnetic field. It doesn't have a nice north-south pole, plus minus, simple like the Earth. In fact, it doesn't have that at all. It has remnant magnetic fields in the crust from a time when it did once have that dipole magnetic field, but now it's this complicated mess of pluses and minuses with complicated geometries. And so when our radar flies over these areas and we're doing this ionospheric sounding, that's where we see the ionosphere all distorted. Remember, the ionosphere is charged, it's susceptible to magnetic fields, and these magnetic fields are changing rapidly, and so you get all of this kind of topography on the top side of the ionosphere. Now, there are also these things called electron-cyclotron echoes, and I won't explain what they are because I don't really understand it myself, but in any case, it's represented by these lines going across here. And the distance between those lines depends on the strength of the magnetic field wherever the spacecraft is at that time. And it turns out that MARSIS, by measuring that parameter, is a magnetometer. We didn't really think that we'd be measuring the magnetic fields of Mars, at least not in this particular way. But sure enough, we are. And actually, we're a very sensitive magnetometer, and we can do it at very high altitudes. And as you can see, as we go from one to the other, you see how these horizontal lines get very close together? That's because the magnetic field there is much stronger. This electron-cyclotron period is much shorter. And we get this amplification effect where every, multiple times per second, we see these electrons coming back to the radar. Now, we can show this in an animated fashion with sound, I hope. So cue the sound, turn up the volume. Oh, it's loud. I can hear the buzz. Okay. Now, what to watch for here is as we are flying across this region of complex magnetic fields, you'll see the ionospheric echo here. It will seem to get closer because the spacecraft is getting closer to the planet, and it's in elliptical orbit, and then it gets farther away. But you'll also see these lines getting closer to one another and farther away from one another. Turns out that the frequency of this electron period effect is very close to the audible frequencies that the human ear is sensitive. So our clever friends at the University of Iowa, Don Gurnett being principally among them, he is the master of turning space data into sound. And he did it again, and I think it's really neat. So we'll run it, and you'll hear the strength of the magnetic field as detected by MARSIS as we fly across. Yeah, beautiful, huh? Okay, on that note, then I'll wrap up. I'll just say a few words about where we're going next. As I showed, we got a beautiful view of the south pole of Mars, and now we're exploring the southern hemisphere of Mars. And we'll continue, but basically we'll be out of that phase of the mission by around the 1st of June. We kind of take a break then because the orbit drifts into the day side, and the ionosphere doesn't really allow us to observe. Actually, the spacecraft is going into a little bit of a hibernation for a while there too. But then come November, we get over the North Pole, and things start to get really interesting again for us. Meanwhile, on Mars Reconnaissance Orbiter, there is another radar sounder. It's sort of the sister instrument to MARSIS called SHARAD for shallow radar. Also a joint effort primarily from the Italian side, but they're flying on our American lander. American rover? No, American orbiter. Let's hope it doesn't land, right? In any case, around the same time, September, October, we'll be turning on this radar on Mars Reconnaissance Orbiter, which is a higher resolution, higher frequency radar focused on the shallow subsurface. We are going to be throwing everything we have radar-wise at the North Pole of Mars this fall, and it's going to be really interesting. We'll complete our first global cycle of mapping by about January 2008. That's when we will have had basically one Mars year, one round of all of the latitudes of Mars. And we're hoping, because by no means will we have looked everywhere, we're hoping that there will be a further extension of the mission beyond that so that we can fill in gaps and also look at some of the places that caught our eye the first time around, optimize our setups, get this high resolution data, do all the things we can to really, really understand further what those interesting places are telling us. So with that, I'll end, and thank you very much. And I don't know if there's a time limit on the room. It's 8 o'clock. If you really have to go, that's 1 hour. That's your limit. You may go. But I imagine there's a few questions out there, so please raise your hand and yell out the question. Yeah.
Is this radar technology useful in finding minerals, particularly oil?
Yeah, the question is, well, maybe everyone heard, but do you mean on other planets or on the Earth? On the Earth, okay. Similar techniques are used on the Earth in industry, in all kinds of industries, including the mining industry. Actually, the most productive version of this technique in the mining industry is to use it actually in mines. So not flying over, certainly not flying in orbit, not flying in an aircraft, but actually taking these devices, small handheld versions of these devices, putting them into mine shafts or drilling new boreholes and dropping these little radars, because if you have two of these systems and you send the signals across a body of rock, you can often tell, is there ore in there or not. Also for oil exploration, there's some application there. The problem is that if there's moisture of any kind, it tends to end your story right there. As soon as you hit a moist layer, your energy is reflected or absorbed and you can't see beyond that. Most of the Earth has moist soil and also has fairly shallow water tables. So it's not especially valuable a technique for remote sensing on the Earth, except in these very cold and icy regions. In Antarctica, of course, there was the famous Lake Vostok underneath the Antarctic ice sheet near the South Pole, which was discovered with this technique, basically flying an aircraft. Yeah.
You said how there were ice sheets on Mars, but if it's really cold, how does the ice build up?
How did the ice get there in the first place? That is an excellent question. And this is part of sort of unlocking the mysteries of the climate history, what we're trying to understand. There is an explanation for how a lot of this H2O got to the poles of Mars that has to do with the changing orbit of Mars. In particular, you know, both the Earth and Mars are tilted over on their axis by about 25 degrees. And what that does is it creates seasons, right? That's why we have seasons. When the planet's going around like this, and so at one point your North Pole is pointing away from the sun. At this point you're pointing towards the sun. That's summer. That's winter. On Mars, we have the same effect. But what we believe we know about Mars is that it's a little more complicated in orbit. It doesn't have a big moon like we have. It's got Jupiter lurking out there not very far away. It tends to take Mars and put it on its side and bring it back up at much larger values than it does on the Earth. What happens is when you do that far enough, you wind up, on average, putting more sun on the pole than you do on the equator. And we're not in that situation now, but you can imagine that a million years in the past, or 5 million years in the past, we were in that situation. That would have essentially transported that snow and ice from the poles to the equator. Then when the whole system moved back, everything moved back from the equator back to the poles. And a lot of people are pursuing this idea to try to explain what apparently are glacial features at the ancient glacial features near the equator of Mars and the volcanoes around Olympus Mons and Tharsis volcanoes, and trying to understand, is there really this long-term global movement of water? And so the idea would be that we're now in this regime where the poles are closer to being up or down, so they're the coldest part of the planet. They become the traps for the remaining water that the atmosphere can process. Yeah.
Question about the ionosphere. I think you located it at 200 or 300 kilometers.
It's more like, the peak of it is more like between 100 and 150 kilometers.
That was
Yeah.
the
Sorry,
AVS and Phobos, I think, found the F1 peak at about 125, something like that.
Yeah, that's right, yeah.
So is this the same or change in solar activity?
No, it's very consistent with the previous measurements. But what we see, actually, it's interesting you mentioned solar activity, is there is, of course, the 11-year sunspot cycle, which tends to change how the amount of solar wind pressure acting on the ionosphere, the content of the solar wind changes. Also during solar activity on shorter scales, on days and weeks when there are solar flares, there are swarms of protons that come out and intercept Mars. We're finding those have a big effect on the ionosphere. In fact, it makes it impossible for our radar to see through the ionosphere, even on the night side, during these high-energy particle or charged particle swarms that come to Mars. So the sun is really a player in all of this, and we're just beginning to understand what those effects are. Anyone else? No? Okay. Thank you all very much for coming.